So the next important question is, how do we know that there is a difference? Okay, where do we draw the line? How do we know that the sampling error is due to chance or due to difference that is based on different population? So if the mean pulse rate of the sample were say 83, the researcher would probably conclude that this difference was due to chance. Because if we look back from situation A, the beats per minute is 82. Okay. So if the sampling say is 83, so you would probably conclude that this is just due to sampling error, because every time you do sample, there's always a sampling error. So you would not right away reject an hypothesis, right? But if the sample mean were say 90, so the off is 8 points, then in all likelihood the researcher would conclude that the medication increased pulse rate of the users and would reject an hypothesis. But that 8 point off or 8 point difference is not absolute yet, because you're going to compare that difference with respect to the standard deviation. So 8 point could be large or small depending on the base of the distribution. So either the null hypothesis is true and the difference between the sample mean something and the population mean, which is 82, is due to chance or something error. Or another possible outcome, the null hypothesis is false, meaning it's not 82 anymore. Okay? And the sample came from a population whose mean is not 82 beats per minute, but is some other value that is not yet known. So for the effects of the drugs, it could be greater than 82 or less than 82. Okay, so uh, if indeed there is an effect from the drug. So how do we answer this? How do we know where to draw the line? So to answer that question, let's take a look at the figure shown. So at the top, we have the distribution of some means, right? So the distribution of the sample means. So we know that the population mean for the beats per minute is 82, and that is the assumed mean of the population. So this is the distribution of the sample means. And if your one sampled mean, x bar, is situated on this uh, location that is far to the right or far from the center to the right, then it's not more likely that it is due to chance alone. So it could also be that because this point or this sampled mean does not really belong to this population, but it belongs to some population, which is the distribution or the population curve at the bottom. So the farther away the sample mean is from the population mean, the more evidence there would be for rejecting the null hypothesis. The probability that the sample came from a population whose mean is 82 decreases as the distance or absolute value of the difference between the means increases. Okay? Because yes, if you do these sample or sizing sample sizes, so sometimes you get different values, not just sometimes, but all of the time. But sometimes you get far different value. So some of them can be due to error, can be due to chance, pure chance. But if it happens most of the time, then it probably not due to chance anymore, but because it probably belongs to some population. So, for example, let's go back to to Einstein or Newton or any other notable figures. whose IQs are far above from the population. So if we put Einstein or Newton in a population that is, let's say, your section or the whole TUPV student tree, and it just happens that we sampled Newton, and his IQ is really to the right of the distribution, then it may be just due to error. But if the gap, okay, that is the mu x, the distance, and that value of the IQ of Newton is so wide that it's very close to the far right of the tail, then it probably does not belong to this population. It probably belongs to a different population. Okay, so maybe this is the IQ distribution of other groups of people. Okay, so even though it is higher with respect to this population, but in this population, it is just an average. Okay, so that's one possible scenario. So this decision is not made on feelings or intuition; it is made statistically, meaning the difference must be significant and in all likelihood not due to chance or error. Here is where the concepts of statistical test and level of significance are used. Okay, so a statistical test uses the data obtained from a sample to make a decision about whether the null hypothesis should be rejected or not. The numerical value obtained from a statistical test is called test value. So there are four possible outcomes when you do hypothesis testing. Either you get the correct decision or you committed an error. So for correct decision, it's either the null hypothesis is false and you rejected the null hypothesis. So you made the right decision. Another right decision is that the null hypothesis is true. Okay, it is true, but and you did not reject or you failed to reject the null hypothesis. So that decision is still correct. So for incorrect decisions or errors, of course, if the null hypothesis is true but you rejected it, then that's an error. And that error is called type 1 error. And the numerical value for that is equivalent to alpha, or what is called that? The complement of the significance level, or the level of significance. Okay, so alpha is the level of significance. Another error is when the null hypothesis is false, but you did not reject it. So you committed the type 2 error, and the numerical value for this is beta. Alright? So alpha for type 1 error and beta for type 2 error. So what is level of significance? Level of significance is the maximum probability of committing a type 1 error. So for example, if your confidence level is 99, 95, 90, so your corresponding level of significance is 1, 5, and 10. So confidence level, level of significance. Confidence level is the probability of being right. The level of significance is the probability of being wrong. In this case, type 1 error is alpha. Okay, so the probability of type 2 error is symbolized by beta. In most hypothesis testing situations, beta cannot be easily computed, but alpha and beta are related in that decreasing one increases the other. Yeah. So if you reduce the probability of committing type 1 error, you increase the probability of committing type 2 error or beta. Okay, so let's continue. Some terms: critical value, critical or rejection region, non-critical or non-rejection region, one tail test, right tail test, or two tail test. So I think it's better just to show these uh, terms uh, in the drawing. So we have three cases. It's either two-tailed, right-tailed, or left-tailed. And we have two regions, the non-critical region and the critical region. The non-critical region for right-tailed is this. So that depends on the significance level. So for the non-critical region for the left-tailed, this is it. And for the non-critical region for the two-tailed is in the middle. And this part, these are all the critical regions. And the corresponding value is called the critical value or the CV. This is the CV, this is the CV, CV, and another CV. So the basic idea of hypothesis testing is that when the test value falls on the critical region, you have to reject the null hypothesis. Otherwise, you have no choice but to still accept the null hypothesis. That's why it's called non-critical region and critical region. So let's do some example. This is not yet a worded problem, but learning how to use the table. Although in this example, his, it was suggested that you have to use the table E in Appendix C, and the instruction is find the critical values for each situation and draw the appropriate figure showing the critical region. So letter A, a left tail test with alpha 0.1. So if we're going to do that, left tail, so this is alpha, just 0.1, so this is 0.9. For letter B, two tail test, so the total is 0.02, so this is 0.01, and this is 0.01, and this is 0.98. And for test C, right tail test, this is 0.005. Therefore, this is 0.995. Okay, so I suggest that that you have to do this first before using the table. So even though the table here is table E and appendix C, that's cumulative. Cumulative. Actually, you can still use the Z table that we used in our previous lesson. So let's try to. I think it's better just to show this. Okay, so first 0.9 and 0.1. So using this 0.9 and 0.1, this is cumulative. So for the left-tailed, amo na siya. For the right-tailed, amo na siya. Okay? So 0.1 and 0.9. So first, tulok ko na lang ang 0.1 because 0.1 is the area. So ano siya? This is 0.1. So makita na di 0.1 the value bilang 0.1 din. Ano yung 0.1? 0.1003. So that is negative 1.28. Okay? Negative 1.28. So dali, ang C beta is negative 1.28 using the cumulative nga table. Let's do for this too. 0.01. Okay. 0.01 mas gamay siya. Ano siya? 0.01 ano siya? 0.0099. That's almost 0.01. That's negative 233. Negative 233. So this is negative 2, 3, 3. So since it is two-tailed, so mo only siya positive 2, 3, 3. And the last is 0.995. 0.995 arithmetic because siya, ano siya to the right. 0.995, I think siya. 0.9949. So that's 2.5, 2.57. This is 2.57. So those values were determined using the table of cumulative. But what about using the familiar table, which is the z distribution? Again, they are just the same. But in this case, no, we have two types of table. And as I have told you before, my favorite table is the one that is based on the middle. The other one, the z table, actually, this is the same as the cumulative. It's just they are same. So here to the right, here to the left. So what I'm going to show you na lang is the this kind of table. So for the first, we have zero point zero 0.01. So if it's zero point zero 0.01 from the center, therefore this is 0.4 because 0.5 and half. So 0.4. So I have to look for 0.4. So 0.4, where is 0.4? Here is 0.4. So siya. 1.28, right? 1.28. This is 1.2, this is 8, so 1.28. Siya, 1.28. So 3, islam mo lang siya. Tangan mo lang siya negative 1.28, but because it is obvious that it is to the left of the center. Now, for the letter B, this is 0.49, okay? So I have to look for the 0.49. 0.49 is here. 0.49. So that is 2.33. Yes, again 2.33. So negative 2.33 here, negative 2.3, positive 2.33 there. And the last, this is 0.005, therefore this is 0.495. So I have to look for the 0.495. 0.495 is here. 0.495, that's 2.5. Ano siya ba? 2.57 or pwede mo 2.58. Okay? Because they are just equally distant. 0.001 naman ang difference but from 0.495. So it's either 2.57 or 2.58. Okay? Okay, so you don't need to use table E because table E is just the same as the familiar table C that you have been using all this time. Okay, but what I've showed you here, I have shown you here is how to use the ano, the other C table from the center. Okay, so let's continue. So for the applying the concepts, I don't have to answer this part. What I want you to do is to read this and try to answer the questions. And if you cannot answer the questions, there are answers, man, in the following slides now. So the reason why I put the concepts in here is because they are very important now. Conceptual ang iyang testing.